Okay. I want you guys to go ahead and take a look at what I have on the screen here. All right. We are now done with basically our historical overview of atomic theory. Okay, so what we're talking about here today is we're talking about what does the nucleus, this thing that Ernest Rutherford kind of discovered, what does it really look like, and how is an atom structured? And we're not just talking about this because we're not talking about this because it's just another fact to learn. The structure of the atom is important in understanding how atoms bond, how this chemical and this chemical create this chemical, how things on the periodic table, how are they organized, and how do we know how they behave, okay? Some of this stuff will be useful to you. Some of it you won't find to be all that applicable in life as you get older. But there are a lot of ideas here that are useful. For instance, why are all batteries made from lithium and potassium and magnesium and stuff from the very beginning of the periodic table? Why are all of the metals used in jewelry kind of in the center bottom? Why is everything that's pretty much radioactive at the bottom? Why are all of the gases that we are familiar with up in the upper right-hand corner? Okay, and so the more we get to know about atoms, the more we'll understand that. The more we understand that, the better we understand the world that we live in. Atoms really do play an important role in how things move, and understanding cells and biology and understanding processes in the body. Everything from the way our neurons fire, that is literally based on sodium and potassium, 11 and 19. Okay? Without sodium and potassium, we'd be limp. We wouldn't be able to function. There'd be no such thing as a brain cell. Okay? Those two elements make it possible for neurons to fire. And when neurons fire, that's how your brain communicates with the rest of your body. So why those two? That's the kind of stuff that understanding an atom helps us to understand. So this is not just we're going to learn this vocabulary word, this vocabulary word, this vocab word, and then memorize it. No, we're going to learn about it so that we can understand everything that follows for the next 15 weeks. Okay? Which is how many weeks we have left in this unit. Because every day it'll be a discussion on atoms. Okay? So, that's the nucleus right there. All right, not so bad, truthfully. Okay, the nucleus is made of neutrons and protons. Okay, why the symbols? Why did I use these particular symbols? Rebecca?
Neutrons and neutrons.
So which symbol did I use for neutral? A zero. The word N for neutron and 0 to represent the fact that it has no charge. Okay, now what about proton? What did I use here, Mr. Reed? A plus, right? And I use the word P for proton and then plus. And so when the neutrons and protons are combined together, okay, they're combined together in this kind of arrangement, all right? And it's known as the nucleus. Now, it's really three-dimensional, truthfully. If I were to go ahead and I were to copy a few of them, I could build, hopefully, what would look to be like a three-dimensional model. So I would do something like this. You don't have to do this, but I'm just going to do this real quick. Is it starting to look like they're overlapping a little bit?
Yeah.
Yep, it's starting to look like maybe there's some layers. Okay, so it starts to get kind of messy, but that's kind of how it works. It's a ball of neutrons and protons clumped together, okay? How many of you have ever pulled out like raisins out of a box before? Yeah, you never get them in a single bit, right? You kind of dump them and all of a sudden they just come out and they're like, boom, and there's a giant clump of raisins and they're kind of all stuck and mushed together. And so you kind of start peeling one off and chewing it at a time, or you just toss the whole clump in your mouth and go to town, right? It's the same idea here. They're clumped together in the center of the atom. That's a nucleus. Small, dense, positively charged central mass in an atom. Why is the nucleus as a whole positive? Yeah.
Because the protons override the neutrons.
Right. The protons have the overriding charge. Neutrons don't contribute in that way at all. Some people are even like, well, what does a neutron even do if it has no charge? And the answer is it stabilizes it. Protons and electrons, they're crazy little buggers. I mean, they just kind of got all kinds of little energy, and they go, whoa, 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 zip, zip. And protons are sitting there, and they're vibrating, they go, ooh, I'm ready to go. And neutrons are like, hey, everybody, put the brakes on, okay? You guys calm down over there. You guys, stay over here, okay? And so neutrons are kind of like the stabilizing link for an atom, all right? They're the glue that's kind of holding it all together. If you don't have the right number of neutrons, you have an unstable nucleus. And that leads to what? Does anyone want to take a guess? Yeah. Radioactivity. That's correct. I will tell you, and now let's just write this down because I think this is an important idea. Smaller nuclei, the spelling might be questionable, have a tendency to be more stable. Okay. Whereas larger nuclei yeah, I don't think that U is supposed to be there. But now it looks like nucleus. Yeah. Zoom in here. And boom. Larger nuclei have a tendency to be less stable. I will also tell you that as you get further down the periodic table, nucleuses get larger. So why would all the radioactive material very much be at the bottom of the periodic table? Ethan? It's because, well, yes, actually, they are technically considered heavy metals, but why do we call them heavy, and why are they radioactive? Yes? They have the larger nuclei, or nucleuses. Yeah, absolutely. Okay, it's like saying a thumb is one nucleus, and then maybe the largest one would be like the size of this room. Atoms can vary greatly. Okay, so it's like having an Ethan Wetland and an Evan Adams. I mean, you just never know. We have like unstable in the back, stable here. Okay, it's just how it works. Small and stable. Not large, but larger. And completely unstable. Okay? Same idea. Just think of your peers. You'll totally got it down. Okay. So, small nuclei, more stable. Larger nuclei, less stable. And this idea of the nucleus does kind of help us understand then what different elements look like. Okay, so this whole idea of small and large, but also the number of protons. So I am going to kind of switch to a different slide here for a second. Now I want you to write this stuff down. I'm going to zoom in here first on the protons part. Okay, protons are positive, and that is true. We've already identified that. But I want you to write these three examples down. 1 proton, hydrogen. 2 protons, helium. 13 protons, aluminum. What am I getting at here? What am I getting at? Yeah.
The amount of protons in the atom turns the size of the atom.
That's exactly right. It's like perfect answer. The number of protons in the nucleus tell us what the atom is. I mean, that's exactly right. So, if it has 1 proton, and let's look at the periodic table for just a second. If it has 1 proton, it's hydrogen. I want you to notice that there's a 1 here on hydrogen. If it has 2 protons, it's helium. Notice the 2 on helium. If it has 13, notice the 13, it's aluminum. The big numbers here, the red numbers, or the little numbers in the corners on here, the number of the element tells us the number of protons it has. Yeah?
Is that its atomic number?
That's its atomic number. So when we're talking about unknown atomic elements, we just haven't put the number of protons together successfully yet. Think about it. Everything that is synthetic is something we've been able to take some protons and glue them together. Take and throw 96 protons together and you've got curium. Take and put 104 protons together and you've got Rutherfordium. We can make it in a lab. We take a bunch of protons, we fuse them together, we make the nucleus, the electrons come around, and we've made an element. We've made an atom of that substance. This is not an easy process. I make it sound like we just get out some Elmer's glue and start hitting them. Grab me another proton, guys. Get them from the storeroom. No, it's not that simple. It takes really advanced equipment to do this. And some of these elements only live for 100th or 1,000th of a second. Because then we haven't got the neutron part right, and so what happens? They're stable or unstable? They're unstable and they fly apart. Okay? So the idea here is that protons tell us what we're working with. So which element has 6 protons?
Carbon.
Carbon, the basic building block of life. Okay. What about oxygen? This was one you're going to have to know eventually. Will has 8 protons. Very good. All right. And neutrons, just for your own purposes, two atoms of the same element can have different numbers of neutrons. That's important. So like all carbon atoms everywhere have 6 protons. But you may have heard of carbon 12 or carbon 14. Carbon 13 is quite rare, etc. These are variations of carbon that have different neutrons. There are 3 different variations of hydrogen. Okay? All right. That's good for today.